In problem 1, we are told a particle moves along a horizontal line according to this position function. This tells us the displacement in time t seconds greater than or equal to 0, and it's measured in meters. We'll say on this number line, movement to the right is positive and movement to the left is negative. With this information, part A says, find an expression for the velocity function v of t. The way this is defined is, to find v of t, you simply take the derivative of your position function. So if we have t squared minus 8t for s of t, its derivative is 2t minus 8. And I'll note that this has units of meters per second. Again, that's because s is measured in meters, t is measured in seconds. The derivative is a rate of change meters per second. In part B, we're going to use the velocity function from part A to determine when the particle is at rest, moving to the left and moving to the right. Recall that movement towards the left is what we call negative values, and movement to the right is positive values. One way to approach this problem is to, I'll write down the velocity function again. It was 2t minus 8. You can draw a simple graph of this function and just indicate where the function is 0, positive, and negative. So I'll sketch the graph of v of t over here, and it'll just be a very simple sketch. So the function is technically defined only from 0 to infinity. It's a linear function, and this is the y-intercept. So I'll just mark that, okay, well here is the y-intercept of the function, that's at negative 8. And I know the function has slope too, so it increases like this. And here's my basic sketch of the function v of t. If your velocity is 0, the particle is at rest. If your velocity has negative y values, negative means movement to the left, and if the velocity has positive y values, that means movement to the right. So I'm going to start with addressing when is the particle at rest. I will note that this is when the velocity equals 0. We have a formula for this function. So that's when 2t minus 8 is 0. We can simply add 8 and divide both sides by 2, and we get 4. And I'll be careful here to note that this is 4 seconds. So this is when my particle is at rest. And actually, I'll also mark that spot right here. This is 4 seconds. Okay, what about moving left? When does this happen? This happens when the velocity is negative. So that is from 0 seconds and including 0 seconds up to and not including 4 seconds. So that's from here to here. Those, again, are values from 0 to 4. So below the graph, I'm going to just note that from here to here, the velocity is negative. And that means moving left. So over here, I'll record down that that was the interval from 0 to 4. And I'll note that this is also in seconds. And this is my answer for moving left. And the last part is moving right. When does that occur? Again, I'll be careful to note that this is when the velocity is a positive value. So this is when my velocity is positive. We record down the values of t for which this happens. This is starting at but not including 4, moving towards positive infinity. So the interval is from and not including 4 up to infinity, also in seconds. And maybe on the graph, I'll highlight this as well. So from 4, moving in the positive infinity direction, this is when v of t is positive. Again, that is moving right. In part C, we want to find the total distance the particle traveled from 0 to 10 seconds. For this part, I think it's helpful to actually draw the number line on which the particle is traveling. We'll need the function s of t. This told us the displacement from 0. So that function was t squared minus 8t. So if we start at 0 seconds and put that into this function, we get 0 squared minus 8 times 0. This is equal to 0. And what this means is our starting point is right here. This is s of 0. I'll draw this above the number line just so it doesn't get too messy, but this is where the particle begins. I'm also going to draw the graph of the velocity function. The velocity function of v of t was equal to its derivative, 2t minus 8. And again, a simple sketch of this function is this linear equation here. And it equaled 0 at 4. Wherever this is negative, your particle starts to move left. So the particle actually begins by moving towards the left. It'll slow down and eventually stop, and then it starts to move to the right because the velocity is positive. Because there is a change in direction, meaning the velocity went from negative to positive, we have to be careful in how we figure out the distance. Here's how I'll do it. I know where it started. Again, that was s of 0. I want to see how far it goes left. That means I should next figure out, well, where is s of 4? So where's this particle after 4 seconds? That is 4 squared, which is 16, minus 8 times 4, which is 32. So this is 16 minus 32, that's negative 16. And again, to be careful, I probably should note that this is in meters and this negative 16 is in meters. So the particle started at 0, and then it moved to the left until it got to negative 16, and that was equal to s of 4. This is when the particle stops, and then it starts to go in the opposite direction. How far does it go? Well, we want to see how far it goes up to 10 seconds, so I'll figure that value of s out next. So s of 10, that is 10 squared minus 8 times 10. Okay, that's 100 minus 80. And that's equal to 20. And that's 20 meters. So now it's over here. So here's 20, and this is s of 10. So the particle goes right up until here. We're looking to find the total distance. For simplicity, I'll call this length d1, and then I'll call this length d2, the one above it. The total distance, so the distance that we're looking for is equal to d1 plus d2. So what is the length from 0 down to negative 16? I'm going to call that 16 meters. I would never use a negative number when referencing distance. So this is equal to 16 meters for d1. Plus, okay, so for d2, we're going from negative 16 up to positive 20. So that means we went 16 and 20 more. That's 36 meters. We add those two things together, and we get 52. So the distance traveled between 0 and 10 seconds is 52 meters. The thing to be careful out here is you have to see the direction that the particle is traveling. If it ever changes directions, you'll have to break it up into parts and then find the distance of those individual parts and add them together. In problem 2, we're going to take the derivatives of the following functions, and I'm not going to simplify the answers. Starting with f of x, that's tangent of this expression, which is a fraction. Here we have a composition of two functions. This means that you have to use the chain rule. We'll multiply by the derivative of this thing in the rectangle. Now, this thing in the rectangle is a fraction, so what I'm going to do is use the quotient rule when I take the derivative of this piece. So the process will look like this. If you want to find f prime of x, we start by taking the derivative of tangent. The derivative of tangent is secant squared. And we leave the inside thing alone. We're like pretending that this is acting just like a variable x. But then we say, well, the thing composed in the function wasn't x. It was much more complicated. For this reason, we have to multiply by the derivative of this thing. Again, I said it's a fraction, so I'm going to use the quotient rule. The quotient rule is the derivative of the top, the derivative of x is 1, and then we multiply by the bottom. And I'll just copy down 1 plus 2x plus 3x squared. We then subtract off the top and multiply by the derivative of the bottom. The derivative of 1 plus 2x plus 3x squared is 1 goes to 0. I won't write it. The derivative of 2x is 2, and the derivative of 3x squared is 6x. This is all divided by the denominator squared, and I don't do anything to the denominator. I just simply copy it down. 1 plus 2x plus 3x squared. Unsimplified, this is the answer for the derivative of f. I'll note that we used the chain rule, and that's because we had a composition of functions. The other rule that we used here was the quotient rule. And that's it for this problem. To take the derivative of the function g of x, here I have x minus x to the 5th to the 1/3 power, and it's being multiplied by arcsine of x to the 7th. I'll note that we have a product of two functions. That means I have to use the product rule. But then also in each product, there's a composition of functions. I have x minus x to the 5th raised to the 1/3 power. And then with arcsine, it's really arcsine of x to the 7th. So the product rule says that, well, you start by taking the derivative of the first. When I take the derivative of this function, because it's a composition, I'll have to use the chain rule. The same goes for this function here. To start with, g prime of x is equal to, okay, it's the derivative of the first. I'll start by bringing down the 1/3, and then I copy down the inside. And I subtract 1 from the exponent. So it's really 1/3 minus 3/3. That's negative 2/3. Now, because it's a composition, I have to multiply by the derivative of the inside. The derivative of x is 1. And for x to the 5th, that is 5x to the 4th. I now simply just copy down arcsine of x to the 7th. Okay, I'm going to run out of space. I'll continue it over here. I'll put a plus sign. So maybe I'll just say, okay, I'm really continuing my work here. Okay, now we switch this around where we leave the first thing alone. That's x minus x to the 5th to the power of 1/3. But now we multiply by the derivative of arcsine. For arcsine, that is 1 over the square root of 1 minus, and it's whatever's composed in the function squared, which is, of course, x to the 7th. By the chain rule, we multiply this whole thing by the derivative of x to the 7th, which is 7x to the power of 6. Here it is. I couldn't fit it all in a single line, so I just wrote it like this here. I'll note that because we had a product, we first used the product rule. And then we also used the chain rule, and that was because we had a composition of functions. In part C, we're taking the derivative of h. If I scan this function, I notice a few things. Again, we have a composition of two functions. We also have a composition here, so we're definitely going to use the chain rule when we take the derivative of this first part, but also this second part. This is the 5th root of 2 to the x plus e to the x. This thing here at the end, this is kind of like a trick. This is e to the power of 7. There's no variable in that, so this is a constant. I write this because I know the derivative of a constant is equal to 0. I'm going to just take a second to rewrite the function h of x. And the only reason I'm doing this is the natural log of, okay, we have tangent inverse, which is the same thing as saying arctangent. There's nothing really to rewrite there. But in this second piece, if you say the 5th root, you're really saying you have 2 to the x plus e to the x raised to the power of 1/5. So for a square root, it would be a half. If it's a cube root, it's a third. Here we have a 5th root, so I put a 1/5. And then we also have this e to the power of 7. Again, I'll just make note that, okay, we got a composition and we got a composition. I'll now take the derivative of h. h prime of x is equal to, for the natural log, it is 1 over whatever is composed in that function, which is arctangent, or as is written here, it's tangent inverse. And the derivative of tangent inverse is 1 divided by 1 plus x squared. The chain rule says that you simply take this and multiply by its derivative. Moving on to the next piece, we will add on. Okay, I'm first going to use the power rule, bring down the fifth, copy down the inside, and then if we subtract 1 from the exponent, that's really 1/5 minus 5/5, that's negative 4/5. The chain rule says we multiply by the derivative of the inside function. The derivative of an exponential function is 2 to the x. If the base is an e, you have to multiply by the natural log of the base. And the derivative of e to the x is simply e to the x. The last thing I'll put at the end, just for emphasis, is plus 0. Let me just write that a little bit better. I think that's really necessary, but technically at the end, when you take the derivative of a constant, it goes to 0. What I'll note is a couple of things here. I used the chain rule here and here. So we have the chain rule. And also, if you have a constant, the derivative of any constant is 0, which is why this value went right here. All right, so that's it for this problem. There are 2 parts in problem 3, but they do not depend on each other, so they can be solved independently. For part A, we're given the function y is equal to cosine of x to the power of 2x. Let's use logarithmic differentiation to find dy dx, or you could simply say y prime. We'll solve for an explicit function of x. I'll copy down the function again. So this is y is equal to cosine of x to the power of 2x. The step I'm going to first do if I'm using logarithmic differentiation is to take the natural log of both sides of this equation. The equality still holds. What I'll do now is take the derivative of this side and set those equal to each other. I will, however, first do the following. There's a property of logarithms that says if you have a log of something to a power, you can bring that power down front, which I'll put right here. Rewriting the whole expression, we have the natural log of y. It's really equal to 2x times the natural log of cosine of x. This is a necessary step. We need this because we don't have a rule that tells us what to do if you have a variable to a variable. You can use a logarithm to rewrite it as a product of 2 functions. To take the derivative of the side, we'll use the product rule. I'll put a product here for emphasis. Starting on the left, if you're taking the derivative of the natural log of y, this is a composition of 2 functions. So for the derivative of the logarithm, it is 1 over y. But by the chain rule, you have to multiply by the derivative of what's inside that function. And what's the derivative of y? Well, it's simply the same thing as saying dy dx. You can put dy dx here, but you can also simply put y prime. So maybe I'll just note that if you're finding dy dx, that's the same thing as y prime, and we're done with taking the derivative of the left side. Now on the right, I have to use the product rule. I start by taking the derivative of 2x, which is 2, and I copy down the second, which is the natural log of cosine of x. I'll add on to this. Okay, so now I leave 2x alone, but multiply by the derivative of the natural log of cosine of x. Now, this is a composition of 2 functions again. So the logarithm says, all right, that's 1 over cosine of x, but then we multiply by the derivative of cosine, which is minus sine. The goal is to solve for y prime. To get y prime by itself, you can multiply y to the other side of this equation. I'm going to do this in the same step where I'll leave this alone on the left side. I'll multiply a y, put it here with some parentheses, and I think I'll clean this up a little bit. Maybe I'll put all this into a single fraction. That is, we have y prime is equal to y times 2 times the natural log of cosine of x. This is really minus. I'll have a single fraction. Then I can write 2x sine x divided by cosine of x. If you'd like, you could call sine over cosine tangent. I'll leave it just like this. The last thing to do is it says express this as an explicit function of x. Currently, this is not set up as an explicit function of x, and that's because we have this y here. How can we replace this so it's just in terms of x? I'll go back to the original equation. In place of this, I will write this. So we have that the derivative y prime is equal to, again, y is cosine of x to the power of 2x, and that is all multiplied by 2, the natural log of cosine of x, minus 2x sine x, all divided by cosine x. And again, if you'd like, you could also just put this as 2x tangent of x. But this last thing I wrote here is the derivative of y. It is expressed as an explicit function of x, and that completes this problem. Part B of this problem, I will also use implicit differentiation, and that's because we have an implicitly defined function. So again, we're solving for dy dx, and if you'd like, just for brevity, you could also say, well, that's going to be the same thing as y prime. The idea is you take this equation and you differentiate both sides with respect to x. I'll start with this y tangent x. This is a product of two functions. Product rule says you start by taking the derivative of the first. What's the derivative of y? Well, it's simply the derivative of y. And then we copy down tangent of x. I then add on to this, leave y alone, but then take the derivative of the second piece, tangent. The derivative of tangent is secant squared. Okay, this is going to be equal to the derivative with respect to x of the other side. What is the derivative of y cubed? It's 3y squared, but by the chain rule, you have to multiply by y prime. So the reason is you bring down the 3, you copy down the inside part y, subtract 1 from the exponent. Because this isn't x, it's y, you have to multiply by its derivative. The derivative of 5x is simply 5. And then this last part is going to be kind of tricky. We have the derivative of e to the xy. Now, the derivative of e to anything is e to that thing, so I'll put e to that thing. But in the exponent, there's a product of two functions. That means we're going to have to use the product rule when we multiply by the derivative of what's composed inside this function. So if I take the derivative of x, I get 1, and I'll leave y alone. I then add on, leave x alone, but now I multiply by the derivative of y, which is simply y prime. Here we've done it. We've taken the derivative of y with respect to x. We'd like to solve for this thing. That'll be a little bit messy, but at least the calculus part of this problem is done. What I'm going to do is distribute this into the parentheses. Everything that has a y prime, I'll move to the left. Everything that does not, I will move to the right. So for my next step, I'm just going to start copying down this entire equation. That's y prime tan x plus y secant squared x. That's equal to 3y squared y prime plus 5. Now I'll distribute in that e to the xy. I'm going to write this as it's 1 times y times e to the xy. I'll put that as y times e to the xy. When I distribute it to the next piece, I'll put plus x e to the xy y prime. Okay, the next step. There's a y prime here, here, and here. I'm going to have all those on the left. I'll subtract this and subtract this to both sides. In the very same step, this does not have a y prime. I'm going to subtract it to the right side of the equation. If I do this all in a single step, I have y prime times tangent of x. I'm going to subtract this first to this side. So we get minus 3y squared y prime. And then I'll subtract this, which is plus x e to the xy y prime. Now, this stays, and so does this, but I'm going to subtract this to the other side. I'll put this as, well, the 5 was already there, and so is the y e to the xy, but I'm subtracting over y secant squared x. Notice that this side has a y prime in every single term, so what I'm going to do is factor it out. And what is left over is, well, we have tangent of x minus 3y squared plus x e to the xy. And the other side I did not do anything to, so it stays as is. And then to get y prime by itself, I'll divide this whole thing to the other side. Here's my final answer. Y prime is equal to, we have 5 plus y e to the xy minus y secant squared of x. That is all divided by tangent of x minus 3y squared plus x e to the xy. And this whole thing, this is the final answer. In problem 4, we'd like to find the linearization capital L of x for the function f of x equals x squared plus 2x plus 1 at a is equal to 2. We will then use this linearization to estimate or approximate f at both 1.99 and 2.1. Notice those two numbers are very close to 2. Maybe I'll write down the formula for a linearization at a particular value. It is a simple equation. It's essentially the equation of a line. If you're looking to find the linearization at some location a, in this case, which is equal to 2, it is f at that value a plus f prime of a times x minus a. It turns out that the linearization very closely approximate the function, provided that you are close to the value 2. So just keep in mind that this formula is really just asking you to find the equation of the tangent line to this function at 2. So we need to know a, which is 2, the value of the function at 2, which is f of 2, and also the derivative of this function evaluated at 2. So to go through those things, a, again, is equal to 2. F of a is really the same thing as saying f of 2, which is 2 squared plus 2 times 2 plus 1. That's 4 plus 4, which is 8 plus 1 is 9. So we have a is 2, and we have f of a, which is f of 2, is 9. We also need f prime of 2. So what is the derivative of f prime of x? That is 2x plus 2. If you want to find f prime of a, you need to know f prime of 2. That is 2 times 2 plus 2. That's 4 plus 2, 6. So f prime of a, which is really f prime of 2, is 6. If I plug this all into this formula, which again is just the equation of a tangent line, we get that L of x, the linearization at a is equal to 2, is f of a, 9, plus f prime of a, which is 6, times x minus a, which is x minus 2. You can simplify this. You could distribute the 6 to both the x and the 2, combine it with the 9. I'm going to leave it like this for now. The reason I'm going to leave this alone is if you're looking to use this thing to estimate f of 1.99 and 2.1, I'm going to note the following. F of 1.99 is closely approximated by L of 1.99. And since we have a formula here for L, I can just put 1.99 here in place of x. This is equal to 9 plus 6 times 1.99 minus 2. I left it written in this form because this subtraction is easy to do. If you take 2 away from 1.99, you get negative 0.01. So this is equal to 9 plus 6 times negative 0.01. If you multiply this by 6, this is negative 0.06. So this is equal to really 9 minus 0.06. And if you subtract 0.06 from 9, you get that this is equal to positive 8.94. So here we go. F of 1.99 through this linearization is approximately equal to this value here. Now, again, what is the value of f of 2.1 approximately equal to? Well, it's approximately equal to the local linearization at 2.1. And you can just take this number and put it here in place of x. That is 9 plus 6 times 2.1 minus 2. So when this one simplifies, okay, that's really 9 plus 6 times 0.1. 6 times 0.1 is 0.6. If you add those, you get 9.6. So here the estimate for f of 1.99 was 8.94. The estimate for f of 2.1 was 9.6, and it came from this linearization here. In problem 5, we're given that if a snowball melts so that its surface area S is equal to 4 pi r squared is decreasing at this rate, 5 square centimeters per minute, can we find the rate at which the diameter is decreasing when it reaches 11 centimeters? We can leave our answers in exact form, so if they depend on pi, that's absolutely fine. I'm going to copy down this formula again. So here I have that the surface area of the snowball, so I guess it's spherical, is equal to 4 pi r squared. So this is the surface area of our spherical snowball. So here's the snowball. It is spherical. It's melting, so its surface area is decreasing. Notice that we're asked a question about the diameter, and this formula depends on the radius. So I'm going to do something here where if you know the radius, r, of the sphere, you can figure out the surface area. But if you double the radius, you'll actually get the diameter. So let's make this connection that if you take the radius and you multiply it by 2, that is equal to the diameter of the sphere. I'm going to use a capital D for the diameter just because when we take derivatives, we use a lowercase d to represent the derivative. I don't want to confuse that with a capital D. I'm going to change this formula so it is expressed in terms of not r, but d. So I'm going to take this equation and actually solve it for r by dividing both sides by 2. I'm now going to take d over 2 and put it in place of r. So s is equal to 4 pi times the radius, which is really half the diameter, squared. If you square a fraction, we'll square the top and bottom, d squared and 4. So s is 4 pi d squared over 4. And the nice thing that happens here is that the 4's cancel, and we're actually left with this nice connection. The surface area of the snowball, or the sphere, is simply pi d squared. With all this being said, what do we know about the snowball, and what do we know about the diameter? Basically, I'm looking at this problem and saying, well, what do these numbers mean? I'm going to start with this 5 square centimeters per minute. This is the rate at which the surface area is changing. So that means ds dt. If you see a rate, it must be a derivative. Another important thing to note is that if a variable is decreasing, if you know it's decreasing or it's stated as such, this is really negative 5. So down here I'm going to say that, okay, not just 5, but negative 5 for ds dt. Okay, here we're asked about when the diameter is decreasing, when the diameter reaches this distance. So what is this number here? That is d is equal to 11. Notice this is not a rate, so therefore it's actually just the variable itself. What is the thing that we're solving for? We want to find the derivative of the diameter with respect to time. This is a thing we don't know, but that's what the question is asking us to find. How do we find it? we go to this formula and we take the derivative of both sides with respect to t. On the left, the derivative of s with respect to t is ds dt. On the right, okay, I have to use the power rule. I'll bring down the 2. We get 2 pi. Copy down d. We subtract 1 from the exponent. It's a 1. I won't write it. But by the chain rule, you have to multiply by the derivative of the diameter, which is the derivative of the diameter with respect to time. The thing that we're trying to solve for is now here in this equation. Notice that we have numbers for both this and this. I'll simply take those values. I'll put 11 here and negative 5 here, and I'll put that work for that over here. So I'll change the color of this just so hopefully it doesn't get too confusing. The derivative of the diameter with respect to time is, okay, I'm going to take this value here, that's negative 5, and I'm dividing it by 2 pi and d, which is 11. Now, what are the units on this? It's important to include them. Since the diameter is a distance, it is going to be centimeters, and that's going to be per the unit of time, which is minutes. So at what rate is the diameter decreasing? Because this is negative, it means, oh, it's definitely decreasing. Now, we don't have to state the negative anymore since it's asking us the rate at which it decreases. I'll just say that it decreases at a rate of, and I think I'll simplify this a little bit. This is 5 divided by 2 times 11 is 22 pi. So I'll say it decreases at a rate of 5 divided by 22 pi centimeters per minute. So again, the important thing to note is when you see a negative here, we interpret that as meaning decrease. If you then write this in a sentence to state, okay, what's happening to the diameter? How is it decreasing? You don't have to then also include the negative here. If you say decreases, you're implying there is a negative next to that rate. In problem 6, let's find the linear approximation of the function f of x is equal to the square root of 1 minus x at a is equal to 0. Again, a reminder of the formula for a linear approximation. It's the formula for the equation of a tangent line. In general, it's f of a plus f prime of a times x minus a. And here we're using that a is equal to 0. So we need to find, well, what is f of 0 equal to and f prime of 0? Once we know those things, we can put them here and 0 in place of a. So to start with, what is f of 0? That is the square root of 1 minus 0, which is the square root of 1, which is simply 1. All right, the second thing we need is what is f prime of 0? That means we have to take the derivative of this function. I'm going to write the function f of x over so it has an exponent. This is 1 minus x to the 1/2 power. If you want to find f prime of x, that is 1/2 times 1 minus x. Subtracting 1 gives us negative 1/2. Be careful here. By the chain rule, you have to multiply by negative 1. That's because the derivative of the inside function, 1 goes to 0, and minus x simply goes to negative 1. So I'll take 0, put it in place of all the x's, and simplify this down. I'll put that here. F prime of 0, it's really 1/2. Okay, 1 minus 0 is 1 to the negative 1/2, and that's multiplied by negative 1. 1 to any power is simply 1, so this whole thing here is 1, but then negative 1 times 1/2 is negative 1/2. So f prime of 0 is minus 1/2. So that is this value here. We have everything that we need to figure out the linearization, the linear approximation to this function at 0. I'll write that down next. Okay, so we have that L of x is equal to f of 0, which is 1, then it's plus f prime of 0. I'll really put minus 1/2, and that's multiplied by x minus 0. X minus 0 is simply x, so I'll just write an x here. All right, good. We have the linearization, and I want to use this thing to figure out, well, what is the square root of 0.98 approximately equal to? To get this number, I have to put some number in place of x. Be careful here. The number that you put in place of x is not 0.98. What number is it? So here, we're trying to approximate this. But we're trying to approximate this by using, first, this function and then its linearization. You have to think about what number you'd put in place of x here, so 1 minus x looks like 0.98. And what number is that? 0.02. If you subtract 0.2 from 1, you certainly get this number here. The reason I'm writing it this way is because it is this value that I'm going to use for x, 0.02. Through the linearization, this is approximately equal to the linearization evaluated at this x, which is 0.02. I will now put this number in place of this x. This is equal to 1 minus 1/2 of 0.02. What is half of 0.02? It is 0.01. And what is 1 minus 0.01? That is 0.99. This is the approximate value of the square root of 0.98. In problem 7, we are told a culture of bacteria grows at a rate proportional to its size. I'm going to note here that that language means dp dt. So if p represents the amount of bacteria, the rate at which it is changing or growing is proportional, meaning equal to a constant, times how many bacteria there are at some given time. Continuing with the problem, it says, the culture starts with an initial number of 200 bacteria cells, and also after 4 hours the culture grows to 300 cells. With this as our assumption, you can use the following formula to model this growth. P of t is equal to P naught times e to the kt. From this problem, we know that P naught is the initial amount, and that is 200. That's given information. We could say 200 cells or 200 bacteria cells. And we're also told that after 4 hours, the culture grows from 200 to 300. If we're using this as our formula, this means if you plug in 4 hours for t, the number that you should get back is 300 cells. I'd like to use this information to find a formula for P of t, meaning find a number for P naught, which we just did, but more importantly, find a value for K, which we called the proportionality constant. I'm going to start by plugging in what we know. P of t is equal to 200 times e to the kt. What we want to figure out is, well, what's K? To figure out K, what you can do is take this information and put it into this equation. If you put 4 in place of t, that means P of t should be equal to 300. I'll simply write this as, if I put 300 in place of P of t, that means you have really put 4 in place of t. So that is 300 is equal to 200 times e to the 4k. To solve for k, I'm going to divide both sides by 200. So I'll divide this by 200, and I'll divide this by 200. And on the right side, the 200s cancel. This is 300 over 200. That's 3 over 2. 3 halves, or I'll just write 1.5, is equal to e to the 4k. If we're looking to solve for k, I can take the natural log of both sides. The natural log of 1.5 is equal to the natural log of e to the 4k. The natural log of 1.5 is simply a number, and the natural log of e to the 4k, that's great. That's actually just equal to 4k itself. E and the natural log are inverses. If you compose them, it only leaves the exponent. I can divide both sides by 4, and I've just solved for the proportionality constant k. From here, I know k is equal to the natural log of 1.5 all over 4. We have everything that we need to define our equation. What is P of t? It is equal to 200, the number of cells that we start with, times e to the power of, and I'll leave it exact, the natural log of 1.5 over 4 times t. I'll note that t is definitely in hours. This is the number of bacteria cells, and this thing is the proportionality constant. In part B, we want to figure out after how many hours will the population reach 1,000 cells. And we can leave our answer in exact form. So that means you can use the number e or logarithms when reporting your answer. You don't have to write it in decimal form. What we're going to do is use our formula P of t. Again, that was 200 times e to the power of the natural log of 1.5 over 4 times t. We're trying to find a value of time when this side is equal to 1,000. I'm going to put 1,000 here and then solve this equation for t, and that'll be our answer. So I will put 1,000 in place of p and set that equal to 200 times e to the natural log of 1.5 all over 4 times t. I'll first divide both sides by 200. On the right side, those cancel, and 200 goes into 1,000 a total of 5 times. What will I do now? I'm going to take the natural log of both sides. In doing so, on the left side, I have the natural log of 5. That's a number. On the other side, the natural log of e to this thing actually just gives us the exponent again. The natural log and e are inverses. So this means we're left with the natural log of 1.5 divided by 4 times t. If you want to solve for t, you can multiply 4 to the other side and divide both sides by the natural log of 1.5. So we get 4 times the natural log of 5 divided by the natural log of 1.5. And that is t. So again, what I did there is multiplied this to the other side, it was here, and then divided this to the other side so it was in the denominator. I'll be careful here and say that t is equal to exactly 4 times the natural log of 5 divided by the natural log of 1.5, and what unit of time do we have? This is in hours. And here is our final answer.